Okay, let's start. Assalamu alaikum wa rahmatullahi wa barakatuh. Good evening and welcome to another webinar series of the American Society of Mechanical Engineers Eastern Saudi Arabia section. My name is Abdulaziz Omar, an officer with ASME SS, and on behalf of ASME SS and all its members, would like to wish you a blessed Ramadan for you and your families. Today, we start our webinar series with a topic on additive manufacturing. Our speaker today is Mr. Omar Abu Hubbaya, the General Manager of Immensa KSA. They specialize in additive manufacturing with both metallic and non-metallic application. The company also provides digital warehousing solution to simplify the supply chain by localizing manufacturing. In the end of this session, we'll have time for a question and discussion afterwards. So please let us enjoy the webinar. Mr. Omar, you may proceed.
Thank you for the introduction, Abdulaziz. أولا رمضان مبارك وتقبل الله صيامكم وقيامكم. If you give me access, Abdulaziz, to share my screen so I can proceed with the presentation. I don't think I have that privilege in Teams yet.
Okay, Mr. Hassan, please.
Hassan, can you hear? Okay, perfect.
The floor is yours.
Perfect, thank you. Okay, please confirm if you can see my slide.
Yes, it's clear.
Loud and clear.
Okay, perfect. Thank you, Abdulaziz and gentlemen for attending our session today. Today I'll be talking about the additively manufactured mechanical parts with instant qualification through the digital warehouse. And just to go through the agenda, we will be starting with Immensa's additive manufacturing introduction and the perspective on digital warehousing. So to start off and kick off with the introduction of what's Immensa and what do we do as a service. So we mainly have three different streams of services that we offer to our clients. Starts with the engineering and design services. The other one is additive manufacturing on demand, and the third one is basically the digital warehousing, or what we call a digital inventory. So we have few use cases and example of each and every service that we provide. For example, recently we have an executed project when it comes to digitization or reverse engineering. A client has missing engineering data, technical information, and there was a part that it was higher. The cost of downtime is very expensive. The part are not available as spare part with the OEM. So the solution that Immensa's provided is basically we took the damaged and the defected part, we reverse engineered it, we converted it into a digital format that is ready for manufacturing. And later on we install it in that digital library to be ready for manufacture whenever the client needs it on demand. And also a recent project that we worked on with Schlumberger is basically a part that the lead time of manufacturing is with conventional way, it takes 16 to 24 weeks. And again, the downtime is too much costly, and to keep that part in the inventory is very expensive. Luckily, with this specific case, the end user has the digital content or the digital files that are ready for manufacturing. So what we did is basically manufacture the part with additive or 3D printing on demand, and it took us less than 3 days. The cost saving on that part was 30%. And there's another example of the digital inventory where a client has many warehouses all around the region, that specifically in the UAE, where they had to keep spare parts stored, and in some cases never get utilized. So what we did, we came in, we digitized the inventory, And we later in our presentation will show you the whole process of digitization and qualifying parts for digital warehousing. And when it comes to Immensa's global on-demand spare part platform, we're trying to partner up with strategic partners and strategic manufacturers. And especially when it comes to material development, machine and technology development, softwares, creating application, be it metallic or non-metallic. So we have our footprint around the region when it comes to our partnership. We also have facilities that are spread in the region. Our biggest facility in Saudi, based in Dammam, where it contains both metallic and non-metallic capabilities. We have another two facilities in the UAE, one based in Dubai that is purely focused in polymer, and the other one in Sharjah, where it's metallic. It's focused on metallic application, and also we're setting up in Egypt and Iraq, mainly for digitization and application creation. Also, we have an office in the state that is connecting OEMs to our platform and bringing in parts to be manufactured locally in the region. We're also ISO certified. We have 4 different ISO certifications, be it in quality, environment, health and safety. We also have the first additive manufacturing oil and gas certification from ISO. We're also Immensa is contributing a lot when it comes to creating standard and qualification procedures, and we are spearheading two GIBs when it comes to service providers. The first GIB was the standard to additively manufacture metallic part for oil and gas industry, and that standard was released back in 2019. And currently, we're developing a second standard that is purely focusing on digital inventory and building a guideline and procedures on how to, from the digitization until the production on demand. We're also part of the ABI 20S to qualify metallic additively manufactured part for petroleum and natural gas industry. And the second standard with ABI that we're currently developing, it's the 20T. It's basically the non-metallic additively manufactured used part for oil and gas industry, and it should be released by the end of this year. Our facility, we contain a number of, as you will aware, additive manufacturing and 3D printing. You're talking about 7 different technologies, and within our premises, we have around 4 to 5 different techniques, ranging from SLS to SLA to FDM and SLM technologies. And we're considering in adding different technologies such as WAM and binder jetting, but that will come in the future. So the process, and just to give you a holistic view about the process of additive manufacturing, on how does it work and what are the value chain of the manufacturing process. Basically, we start with material. There are 500,000 plus materials available for additive manufacturing, especially when you talk about the metallic materials. And there are a variety of machines with different sizes and different applications. And later on we go into the design, and designing part for additive is really crucial. There are many ways where you can design part with an optimized feature to leverage the benefits that additive manufacturing can deliver. And once we finalize the design stage, we take the part into the simulation, where we simulate the part, we simulate its mechanical properties. We ensure that the part is operationally fit to deliver and to be up to the standard and qualification before it gets manufactured, and that's through the CFD and defined element analysis. And later on, we take it into the parameters, and the parameters, creating parameters for additive manufacturing is a whole different ball game. It's a know-how by itself. And creating parameters for each and different techniques, it's really crucial. You cannot just because especially when you talk about material, each material has own speed of laser power. Uh, the in some cases you might require a heated bed, so it varies from application to application, and you also consider the environment where the machine is being operated at. And once the part is being produced and manufactured, there's post processing. In some cases, you'll have to take the part into a heat treating solution, ensuring that the part are meeting the specification and requirement of the client. And in many cases where we take the industrial part and we conduct some testing, be it destructive or non-destructive testing, to ensure the fitness of that part on operation. We'll give you a few examples of parts that are printed at our facilities. Here is a boat propeller that was printed out of stainless steel 316. And this part is now being replaced, and since it's a crucial, a critical part, and you cannot really wait some time, especially when it comes to maritime and logistic, where timing is really crucial. So we digitize this part and we have it ready to be manufactured on demand using additive manufacturing. And here's a short video that shows and gives you an idea of how 3D printing work, especially when you convert it, you compare it to conventional way. Basically, instead of you taking a physical material and then you carve it out, it's basically a powder. You have a powder bed that is, and this is a single technique that's called SLM, selective laser melting, where you are melting layer by layer using a laser power of 400 watt, and you are stitching these layers together, as you can see in that short video. Okay, and this is another application that is relatable to the oil and gas industry. It's a heat exchanger tube insert. This is a tube insert that it's also called ferrules, where it's used to protect the tube sheet from corrosion and erosion. And this parts gets replaced frequently, so we have it digitized and ready for manufacturing whenever it's needed. We're also considering upgrading materials, converting this material from metal to non-metal. Dealing with high performance non-metallic material could really extend the life time for such a component. And here's another application for gear that was printed out of titanium. The weight was reduced quite significantly in this case. And then this is one of our favorite, use case of additive is impellers, a rotating part that is really critical, and it takes a long time to be manufactured conventionally. In some cases, 6 months to a year. Especially when you take it through the conventional way of manufacturing, where you create a mold and then you cast into that mold. That process is quite lengthy and it takes some time. So what we did in this case, we scanned the defected part. We created a digital engineering design that gives you all the parameters, dimensions, the tolerances, and what have you. And we performed the simulation to ensure that the part is being designed accurately. And later on, we performed the heat treatment and the post processing. Basically activities, and once that is done, we conduct the testing and validation validate its performance. And normally what we do in this case, we create testing specimens to conduct our mechanical testing of tensile and compression. It depends on the requirement and the standard that we're complying to. Feel free to interrupt and ask if especially when it comes to these use cases. So now let us jump into the digital warehousing, since it's the core of our presentation here today. So how do you select a part that are suitable for the digital warehouse? Because not everything is replaceable with the digitization process. You need to be very, very selective, and there's a process and guidelines that we comply to when it comes to choosing part that can be digitized in our digital warehouse and printed and produced on demand, either through additive or conventional way of manufacturing. What we're focusing on is basically having that part produced in a timely manner, on the most effective and quality that is demanded by the end user. So the process or the flow of our DIS, or the digital inventory solution, is basically start with the assessment, qualifying the part that are useful for digitization. And once that qualification is done, we take it into the digitization, creating a digital asset and converting the physical part into digital format. And there are different ways and streams of doing that, and we'll come into that later on. And once the digitization is completed, we starting creating the digital asset and ensuring that the digital passport contains the relative information that is ready for manufacturing. And once that digital asset is ready, we take it into the library and to be digitized and stored and manufactured whenever it's needed. And once that manufacturing is done, digitization and the storing of file is done, we produce the part whenever it's needed on demand. So if we take it one by one and we start with the assessment. So the assessment start with evaluating the technical information and seeing what data available either with the end user and OEM, seeing what are the information that either we can obtain from the end user or we can create and allow our application engineers to work on it, to identify the materials, the specification of the part, the geometry, and getting the part engineering drawing out of that physical part, and also understanding the commercial side of it, getting to know how this part is performing commercially. Is it high value? Is it low value? Is it what's the cost of is it not being available in a warehouse? How much is the client is severing if that part is not, and what are the logistic costs? So getting this commercial information data is really crucial to understand whether the part is suitable to be digitized. And then we conduct our own analysis and scoring, and we have a whole mechanism that scores that data and gives you the outcome of A to F, where A is the part feasible for digitization, and F is not really. And the way that we feed and the way that we collect information are based on a number of data. So we can either integrate with an ERP system and massively upload part into the platform, or we physically collect the parts. And as mentioned earlier, we take the part and we reverse engineer it, and we take that technical data out of it. And the information that we extract and we create as data is basically a description of that part that shows what type of part is it. As you can see, we have impellers and the number of the part number and the original manufacturer of that part, the storage location, the dimension of that part, the material, the lead time, which contribute to the commercial side of the analysis, the cost and the part consumption annually, uh, and then later on we compare it to the cost of additive manufacturing if we decided to produce it with 3D printing, and the lead time of additive manufacturing, and the proposed material as an alternative. So we collect that data and then we analyze it. We analyze it through our data algorithm engine, and it tells you and gives you that it builds that category of scoring the technical and commercial side of it. And the scoring, as just mentioned, you score it from A to F based on technical visibility, commercial, and data availability. So we start with A. If it's A, then the part is suitable technically and commercially. If it's B, technically not feasible, but commercial data are available. And sorry, perhaps technical data is available, but not reachable, where you have to convert that part into digital file so you can create that technical information, but commercially are available. C, where technical availability is there but commercially are not. D, you don't have sufficient technical data. E is basically insufficient commercial data, and F, both technically and commercially are not feasible. So these are the categories that we tend to come up with that ensures your visibility when it comes to part selection, because again, not everything is suitable for digitization, and you need to be very careful when you select parts that are convertible from digital to from physical to digital format, and then you have it ready for manufacturing on demand. And so the digitization process normally start with creating that digital passport. You basically 3D scan the files and create a model, a 3D model out of it. You create also something called, you identify the material, you identify the manufacturing standard and the AMC, or the additive manufacturing category. Classification. Is it A, B? We have three different classification. Is it A, B, or C? Where each and every classification, and we'll come into that later, each and every classification categorize the material based on its crucial application and testing requirement. So the digital passport contains basically these are the technical information that we come up with to ensure that the part are ready for manufacture whenever it's needed. We have the geometry, material, manufacturing information, and the business aspect of it. And that digital passport is basically contains in each and every part we digitize. So let's say we have thousands of parts that are we digitize. We have 1,000 digital passports for each and every part. It has its own specific data information that allows it to be manufactured on demand. So then we comes into the scoring and creating, as I mentioned, the AMC 1, 2, and 3 catalog, where basically certify the material based on its crucial application. So one is basically a component that needs to be printed and tested to verify its digital assets. 2 is basically no requirement for testing, but you will have to test the testing coupons to ensure that the part is produced as per the specs. And finally, the third AMC is no need for testing, which in so many cases that part is not it's not really critical. And finally, we have we have our digital platform where we save and contains these data information. We have our part library that shows the part in its software and digital format, and then also we have the dashboard that shows the scale of business insight, and where you can also track the digitization target and tracking of the parts. And finally, we have the marketplace where we can get the RFQ from the end user to produce these parts on demand, and you can also track your order workflow from initiating the request until the manufacturing, and it ends up with the delivery. So the on-demand manufacturing basic workflow, just to give you a full picture. So our clients raise an RFQ through the DIS solution. The RFQ get distributed to our either we do it in-house, or if the capability is not available, we send it to our network and partners of manufacturer. Our client receives a quote with a lead time, and later on we select a vendor, and then the order get placed. A client directly placed the order, and if a vendor and the price is ready and validated for the product, basically the vendor confirms the order, and we have the manufacturing done as per the digital passport, the information that this was created earlier. And later on, based on the AMC catalog, we get the part tested and qualified, and then a report will be generated. And once that part is completed, the part gets sent to the end user. That includes the testing and certification. So that was my full presentation. Feel free to ask any question. Thank you.
Thank you, Mr. Omar, for this informative and valuable session. Now, ladies and gentlemen, if you have any question, the stage is yours. Please feel free to ask.
Marhaba. Hello.
Yes.
My name is Mahfouz from Amman, Jordan.
Yes, Mahfouz.
So, my question is, first, with the digital data of any product, usually you have the data of it's a 3D model, but for manufacturing there is also geometric tolerances that has relationships between each dimension. So you have perpendicularities, parallelism of the part, and we know that with metal manufacturing till today, tolerances from the process itself are not very accurate. So you cannot do a fitting tolerance, 20 micron, 30 micron, 40 micron tolerance is not achievable directly out of additive manufacturing. How do you transfer that data? Do you put that data in the digital passport? How do you do it? How do you create these relationships of dimensions? That would be my first question. And a similar question is about also when you digitize 3D scanning, because with 3D scanning, you also capture the existing geometry and you don't capture relationships and design intent. So you cannot, you capture the size of it, the intended, the real size, but you cannot get the intended size or the intended parameters for that size. So if you cannot capture this area, we have a circularity or a diameter tolerance of G6 or plus minus 20 micron. How can you transfer that data from digitizing an existing product? These are my questions. Thank you.
Perfect. محفوظ ولا؟ Did I get your name right? Mahfoud. Yeah, excellent question, Mahfoud. To answer your first question, when it comes to the tolerance, I mean, this is where the selection of parts comes really, really crucial. And we tend to select parts that are applicable for additive or advanced manufacturing in particular. So not everything and not every tolerance is doable with this technology. So we tend to be very, very selective when it comes to choosing part that are suitable. And the way that we comes about it is the tolerances, it's crucial. So if you have something that is not applicable and we cannot really achieve, and it gets disqualified immediately through our technical assessment. And if it's doable, but it's need to have that accuracy. I think with additive manufacturing, it's a great tool to achieve that geometrical complexity, to achieve what was not being able to be done with conventional way of manufacturing. And there are many ways and there are many techniques that we do, and we have our own recipe, and we have our own know-how when it comes to collecting that specific very accurate tolerance, and it goes into a micro level when it goes to that level of tolerance. And in some, it depends, it varies. So your question basically varies from application to application. There are applications where we collaborate with the OEM to get that data if it's not available within the data sheet. And there are some cases where the OEM is not producing that part anymore, and they're out of the market. So we come in and we have our own tools and techniques that figures out what are the tolerances required for that specific application. And the tolerance is really crucial when it comes to, especially when it comes to this technology in the post production. So the printing itself, you'll tend to get very accurate, geometrical output. However, in some cases, you have to take that part into a post-processing, a machine shop that has to machine and take off some excess material. And this is where we face some challenges, especially when you deal with a third party that is not familiar with the technology. But we tend to work very closely with our partners to figure out ways and procedures to come up with the tolerance required. The last question when it comes to you asked about scanning, I believe, and reverse engineering and getting your high accuracy of geometrical capture. I don't know if did I get your question right?
Yes, it's just the question has, when you scan anything, you scan it as is from reality.
Yep.
But the intention of the designer, there was an intent. So you capture reality rather than you capture the initial design intent of any product. So if you're scanning, let's say, you're scanning, an example, something in plastic bottle. This bottle is deformed through the plastic production. And just to give you my, I have a machine. I'm a mold maker, product designer in plastics, and I have my own machine shop. And I'm studying the options if we can use additive manufacturing in parts of mold making. This is my intent for the questions. Okay, thank you.
Okay. Yeah, I mean, so basically, you are, and especially when you deal with industrial, we deal with industrial parts a lot. The part that we're getting are normally defected components that are obsolete, and there is no existing drawing available in the market. So the way we go about it is, so the reverse engineering is one thing, and you need to have a very strong and capable scanner to capture the geometrical information. However, we tend to take it into the reverse, what we call it, a simulation of part. So we simulate its performance during operation to ensure that we deliver the right quality or the right geometrical information. So I think simulation comes in really crucial, especially when you deal with finite element analysis, doing your mechanical simulation and understanding the performance of the part. And if you're off in your scanning, if you're off in your design of that part, you will immediately capture it, and you can optimize your design to perform the specific operational requirement. So
Thank you.
scanning is one thing, and the other thing is the simulation, and also later on we do prototyping. In some cases we prototype and we produce it with low cost just to see whether it fits or not.
Thank you.
Thank you.
Assalamu alaikum.
Alaikum salam.
And speaking of metallic printed items, what's the limitation in matter of material grades?
The what again? The material grades?
Limitation regarding the material grades, like
Okay.
steel alloys, aluminum alloys, like this.
Yeah. So there are material limitation, especially when it comes to that low value commodity or components, especially when you deal with carbon steel and steel that are not that high of an alloy. It's not really available with additive. The focus is and what we're, and this is why we selecting parts that are high value and high alloy, is to get the materials that are suitable for the technology. Not all materials are available, and we, in some cases, we work with our material partner. We have a partnership with Samvic that develops material for additive manufacturing to do some R&Ds and figure out what material can be developed for this technology. Currently, we're using I think around 15 to 20 different materials alloy. I can share it with you. So the latest material that we developed with, we worked with Samvic to develop is super duplex steel material, the 2507. That was the latest material that we worked on. There are material that are high performance, such as titanium and Inconels that we also work with. So the material options are there. In some cases, we deal with materials that are massively utilized, such as stainless steels alloy. But there are materials that we work with to develop applications, and it's basically based on the demand and the requirement that we're getting from end users.
There is a question, Mr. Omar, in the text from Mr. Amir. He asked, for the non-metallic material you manufacture, are they polymer-based or do you manufacture ceramic-based part as well?
No, it's polymer-based. We also do composites material, composites such as glass fiber and carbon fiber materials. But no, we're talking about purely polymers, materials like PEEK and Ultem, PA11 and PA12. These are the type of material that we normally deal with.
Noted. Any more question, gents?
Yes, Assalamu alaikum.
Assalamu.
Yes, this is an interesting topic about having digital spare parts. It's going to happen sooner or later. But I have a question regarding the. This is not just about producing the part. It's about keeping record for future production. does that create any conflict with other manufacturing companies? Have you faced this issue with other competitors, or how do you plan to manage with this conflict?
So basically, you're becoming an OEM when you remanufacture a part. You become the original manufacturer of that part, because you're using a special technique that is not being utilized. But especially when you talk about the oil and gas, there is not many applications that are when you take a part and you redesign it and you build a digital passport and the information, digital information that makes you able to manufacture that part, it becomes, you become the OEM. And there is no, we did not really face any conflict with the original manufacturers. I don't think there would be any issues in that regard. Actually, in some cases, we collaborate with OEMs to localize their manufacturing here in Saudi. There are OEMs from all over the world who are interested to avail their parts and components locally. So they would rather to come through a contracted manufacturer that are qualified and have the capability to produce this part locally, especially when you talk about spare parts. So you want to get rid of your logistical cost and expense and produce these parts whenever you need it on demand.
Thank you, Omar.
Thank you, Abdullah.
السلام عليكم اخ عمر. انا حسن السلوم. في عندي استفسار بخصوص ال 3D printing. لما يكون مثلا انت يمكن انك مريت you touched based on this subject when you said that the part might be the geometry of the part is not fully intact and that you can scan it with your scanners. So in this situation, what can you propose or suggest to overcome this dilemma?
I did not get your question, Hassan Malish. So can you repeat the question again?
Let me explain to you. For example, if you have an impeller that has been worn out, where you're being asked to 3D print it. So how would you, as مثلا one of the attendees asked you about the tolerances, how would you make sure that you 3D printed the part correctly?
Okay. So there are lots of different testing, and for example, as you mentioned, impellers, we have different type of testing to ensure that the part are performing up to the standard. There are, as you've seen in the presentation, there are different categories of parts. There are critical parts that requires destructive, non-destructive testing to ensure that the parts are being produced up to the standard. And these testing for impeller, for example, we've done a high-speed impeller that require balancing, and you don't have so many facilities locally that does that. So we had to create the testing rig in-house and test the part performance before delivering it to the client. So it varies from application to application. There are applications that requires the mechanical testing of specimens. You take that part, you take that specimen, and you perform the destructive testing of tensile and compression. There's microstructure type of testing where you want to make sure your material up to the performance. There are fraction toughness testing, and we have that long list of testing. It varies from application to application. We tend to follow the standards, either the STMs when it comes to material, to achieve the we treat additively manufactured parts like any other manufacturing process, where we perform the different type of testing based on the application and based on the criticality of parts.
Thank you.
I have a question, if you allow me. Regarding the part porosity, how good is the part regarding the porosity?
Velocity?
Porosity. The holes inside the part.
Yes. How?
Spaces.
Okay.
How good is this technology with it? Is there
Actually,
any
this technology has been so great when it comes to sophisticated holes and passages. In some cases, these passages are smaller than or thinner than a human hair. This technology allows you to produce sophisticated geometry, and basically it reduces your instead of having مثلا two parts connected to each other, and you have different supply chain of production process to produce two parts and connecting them together. No, you get it produced as a device, contacted together using this technology. So I mean, I wouldn't really concern about how accurate the passages or the holes inside the part, because you're using a laser, a selective laser melting technique that is super accurate.
So it doesn't need any centering after printed part?
No, you do. You do need centering. You need to center. It depends again on the not centering. Actually, you'll need to release the stresses with the vacuum furnace. And centering, you would need centering if you use a different technique in this technology, a technique that is called binder jetting. Binder jetting is a powder. You're not using laser. Basically, you're using a powder that is mixed with some type of solution that basically melt or connect the part together. Then you take it into a centering process to release all that solution out of that part. But that's a different technology that we are not really involved in. But yeah, I mean, centering is being used, but not for our technique.
Okay, thank you.
الله يعطيك العافية عمر. I just have one follow-up question, my question in the chat. So why is it ceramic composite not part of your portfolio? You didn't see any local demand for it? Because one of the issues that we see is that, for example, one industry like metal cutting, metal forming industry, I mean, we use cutting inserts, ceramic cutting inserts, and they are exclusively manufactured by Sandvik or Kenmetals. So this is one area, but you don't see any local demand for these kinds of parts.
No, it's not actually the demand. It's actually the technology limitation. There's no technique as of today with additive manufacturing used to produce ceramic material. There are some ceramic application, but mainly in the medical sector. But I haven't seen any oil and gas or industrial based machine that does ceramic printing. I don't think it does exist yet. But if it's if it's been developed, I think there's a huge demand for ceramic, especially when you deal with high temperature and a high corrosive environment.
Yes, I mean, there is no additive manufacturing technique, but there is, for example, spark plasma sintering.
Yes.
Like here in the GCC region, only one, if I'm not mistaken, only one SPS is available, I think, in the KFPM. But it uses powders as initial starting materials for precursors.
Okay.
But not in the traditional sense as additive manufactured metals.
Yeah. I mean, I'm sure there are techniques, but it's not the core of our offering, since we tend to focus on additive manufacturing, and we're trying to cover the whole portfolio of additive manufacturing technique. As of to date, we did not. So I would rather focus on additive, and there are technologies like QAM, binder jetting, and different SLA, different techniques that are not yet been covered, and there is a lot of applications and demand that we would really tap into. So yes, I agree, but that's not our area that's not our area of specialty. But I'm sure there are demand when it comes to ceramic manufacturing.
Thank you so much.
Thank you.
Any more questions, gents? If not, I think we may end up with a special thanks to you, Mr. Omar, and to you guys for being with us in this technical webinar, which we hope it was beneficial session for everyone. And we are looking forward to meet you in the future webinar. Thank you all.
Thank you. Thank you, everybody.